This is sample exam 8, problem number 10. Let x and y be independently distributed normal random variables with mean of the x, I set it equal to 5, and the mean of y, I set equal to 3. And the variance of x is 9, the variance of y is 16. Which of the following is closest to the probability that y minus x is greater than 7? Here we want to find the probability that y minus x is greater than 7. So since y and x are normally distributed random variables, if we subtract the mean of this difference and then divide by the standard deviation of this difference to both sides, then it doesn't change the probability, but it changes this random variable to a z, a standard normal. This is 1, so the probability that z is greater than 1 is 0.16. Number 11. Let x intersect b equal to 0.2. Probability A is 0.6. Probability B is 0.5. Then find the probability of A complement union B complement. Number 11. The probability of A complement union B complement. If you use, I think it's de Moivre's theorem, or however you say it, you get this. It's the same as the probability of A intersect B complement. Well, that is a complement, so that's equal to 1 minus, not the complement. And then this is provided, so it's 1 minus 0.2, which is 0.8. Number 12. Let x be a Poisson random variable with mean lambda. And I change the inequality here. If probability of that x equal 1, given that x is less than or equal to 1, is equal to 0.8, then what is the value of lambda? Number 12. We have f of x is equal to this. They said it's a Poisson random variable with lambda. And we want to find the probability that x equals 1 given that x is less than or equal to 1. And then the denominator here is this one, less than 1, which means 0 and 1. And the intersection of these, that x equal to 1 and x is less than or equal to 1, is just that x equals 1. So you plug in x, the values for x into this equation here, and then things reduce and you get this, and that's equal to 0.8. So then you cross multiply and you get this, and then you take this to the other side, solve it, divide, you get lambda is equal to 4. Number 13. The following table represents the relative frequency of accidents per day in a city. Which of the following statements are true? Now, number 13 is we're given the table and some statements. First, you can't calculate the mean because you need to know each of the accidents or each number in your sample. And since the table says 4 or more, we don't know if it's 5 or 6 or 7, so you can't actually calculate a mean with that table. But you can calculate a median. The median is the probability of being less than some value is greater than or equal to 0.5, and the probability of being greater than that value, greater than or equal to that value, is also greater than 0.5. That's what the definition of median is. Well, in this sample, the median is 0. And then the mode is the highest point, the highest relative frequency, which is at 0. So given these three conditions, the answer is C. Number 14. Let x1, x2, x3 be independent, identically distributed random variables, each with density function f of x equal to 3x squared. Let y equal the maximum of x1, x2, x3. What is the probability that y is greater than a half? Now, number 14, we calculated a few different ways, two different ways, and we want to know the probability that y is greater than 1/2, or y is the maximum. Okay, using the first method, well, in both methods, we need to find the CDF of our distribution, our original data, x. So that is you integrate from 0 to x of our density, then antiderivative, plug in limits, you get x cubed. In the first one, we use order statistic theory. And based upon that, the density for f of y is given to be this. And then we just plug in the appropriate things. So this boils down to 3. F of x, but plug in y, you get, and then square it, you get y to the 6th, and then this is just 3y squared. So this becomes 9y to the 8th. So to find the probability that y is greater than 1/2, you integrate from 1/2 to 1, plugging in our density, antiderivative, and plug in the limits of integration, and we get 511 over 512. Now the second method is we use a little trick. Now, to be probability of y is greater than 1/2, that's equal to the 1 minus the probability that we're less than or equal to 1/2. And now this is saying that the maximum of x1, x2, x3 is less than 1/2. That means that all three of them have to be less than 1/2. So this probability is the same as this. And of course, the 1 minus stays the same. Well, these are independent, so it's the product of those, and so this probability is the same. So you might as well just look at the probability of 1 and cube it, and that's what we do here. And the probability that x1 is less than 1/2, so that, which is what this is, so that's 1/2 cubed, and then we cube it, so that's 1 minus 1/2 to the 9th, which is what we got here, and that's 511 over 512. Number 15, let the random variable x have the moment generating function m of t equal to that there. What are the mean and variance of x respectively? Now, number 15, we want to find the variance of our variable, and we're given the moment generating function. So first we find the first derivative of the moment generating function, and then you take it, it's the derivative of the first times the second plus the first times the derivative of the second, and you get this. Now I rearranged it to this, which, you know, this piece is the original moment generating function, and I call that just f of f of t. Then, because we need the second derivative of this, okay? So I take let's find the derivative of this, which is this piece, which is this. So it's the, I like to take this up, and then it's the derivative of that. Then the chain rule times this, and then it's plus this, which you brought up, times the derivative of that, which is 2. And that you can simplify it to this. So now the second derivative of our moment generating function, which if this is the first derivative, then it's the derivative of the first times the second plus the first times the derivative of the second. And now to find the mean, you plug in 0 into the first derivative. So this is, you plug in 0, you get 1, you get 1, that's 0, it drops out, so 1 times 3 is 3. Now the second moment, central moment, is the second derivative, plugging in 0. So then You plug in 0 here, which we said was 3. And then you plug in 0 to this one, you get 3. Plug in 0 to this, you get 1. You plug in 0 to the derivative, you get 2. It's 11. So the variance is expected value of x squared minus the mean squared, which is 11 minus 9, which is 2. Number 16, a random sample of size 6 is selected with replacement from an urn that contains 10 red balls and 5 white and 5 blue. What is the probability that the same sample contains 2 balls of each color? Problem number 16, we want to find the probability that the sample contains 2 of the same color. So we have red, and the probability of red is 1/2, probability of white is 1/4, probability of blue is 1/4. Now we're sampling with replacement, so this is a classic multinomial. So we want 2 red, 2 white, 2 blue, and you plug it in. So it's our sample size is 6. We want 2 of each color, and then we want 2 of each, and then that breaks down to 45 over 512. Number 17. The observations y1 through yn are to be fitted with the linear regression on the constants x1 through xn. If y bar is 6, the sample variance of y is 36. The correlation of x and y is 14. X bar is equal to 3. Sample variance is 16. What is the least squares predicted value y hat for x equals 3 over 2? So in problem 17, they ask us to find the least squares estimate for when x is equal to 3 over 2. So here we derive it from scratch, and I point out a few spots where you probably should just memorize it as opposed to deriving it, but I like to derive it. So least squares error. So this is the error term. So if we subtract these to the other side, then we get the error is equal to that difference. And that's what this is. And we square it, and then we sum it for all our data, and this is the sum of squared errors. Now we want to minimize this for choices of B0 and B1. And so we take the first partial with respect to beta naught or beta 0. So you take the derivative, so the 2 comes out front, and then it's 1 minus that. And then it's the chain rule with derivative of this, which is minus 1. We set it equal to 0. Now this is a constant, so we can take it to the other side. That's a constant, take it to the other side. So here we get the sum of the y's, and then we get n of those, and then we get beta 1 times the sum. Now we take the beta n beta 0 over and then divide by n, and we get this. Now the n can be divided by both sides, and the sum of the xi's divided by n, well, that's y bar. In the same way we get x bar here. Now this is a formula that you could commit to memory. It's pretty easy to memorize too. So now let's find the partial of the sum of squared errors for beta 1. And then, you know, the 2 comes out front, it's 1 minus, and the chain rule, you get minus xi. We set it to 0. Bring it up. And then this 2 can go the other side. The negative can go the other side. So then when we multiply this in, we get the sum of xi, yi. Oh, and for beta 1, we put in this. So we plug that in here, which is what this is. And now it's times the sum of the xi. And then here we get beta 1, sum of the xi squareds. So in this problem, so we multiply this into both sides, and then we take anything with a beta 1 to the other side. So here, so notice that for this, I could divide by n and multiply by n. Multiply by 1 doesn't change it, but that makes it n times x bar. So when you multiply this to that, you get this. And then that would be x bar squared, n times x bar squared, which is this. And then we factored out a beta when we took the other side. And then we divide by that. Now, this is the formula for beta 1. It's the cross product, or and then it's divided by the variance of x. So this one here is, so this is the sample covariance divided by the sample variance of x. And since this one is divided by n, we have to put a divide by n up here. But in this formula, there's no divide by n. But you could. If you divide this by n, that's the sample variance. And if you divide this by n, that's the sample covariance. And then we take this and multiply it by 1. So sx over sx, sy over sy. So those are just 1. And then the original is still the same. Well, this is given in the problem as 1/4. So, and then these are given, and that's equal to 3/8. So then our formula for beta 1, we have to plug in our value into the formula, and we get 39/8. So now we find the least squares estimate of 3/2. So y hat and beta naught hat plus beta 1 hat. And then we just plug in the values we calculated and we get 87/16. Number 18. A single observation is taken from a distribution having the density function f of x theta given there. For x between negative infinity and infinity. For testing the null hypothesis that theta is equal to 0 against the alternative that theta is not equal to 0 at the 0.05 level of significance, the likelihood ratio test has the rejection region what? Also note that the integral of dx over 1 plus x squared is the inverse tangent of x plus c. Now what? Oh, that was problem 17. Now problem 18 is kind of fun. And we don't have to do all this derivation because they give us a nice big hint, but I'm going to go through it just for fun. Now this is pre-work. So if this is a unit circle, then every dot on this unit circle can be, every point can be considered cosine of x, sine of x, where x is the angle between the axes. And so to find the graph of the tangent of x, which is this ratio, you can think about it. So when the point comes down here, so x is 0, then this is 1 and that's 0, so the ratio is 0. And then as we go to pi over 2, so as this comes up to here, then the sine approaches 1 and cosine of x actually approaches 0, so it vertically asymptotes at pi over 2. And then if we go backwards, it's just the opposite. So sine of x approaches -1 and cosine approaches 0, so it vertically asymptotes at negative pi over 2. So this is the sine, and then it just repeats. Now the inverse of this, what you do is you take a dotted line, which is here, and then you flip this half for that half and that half for this half, which you get this. So you take these two and map it over, and those two and map it back, and you get this. And so that's the inverse tangent of x, often called the arctangent of x, same thing. So there, as x gets big, the inverse tangent limits to pi over 2. As x goes to negative infinity, the arctangent limits to negative pi over 2. So we will use this fact. Now this is the hint that they provided. They provided this interval has a certain answer, but let's derive it. So here, let's let x equal tangent of theta, and then the derivative is this. The derivative of that is this. And now you can derive that because the tangent is sine over cosine, and then everybody knows those derivatives, so it's a derivative of the ratio, and then you can derive that. So now we plug in the value. So that's this tangent. But the derivative of x is this, so that's this. And then, but you can show that 1 minus the tangent is just the secant squared. And then that's 1, so you're left with this. And the antiderivative of this is just theta plus a constant. Now we have to find what theta is in terms of x. So here we have this relationship here. So to solve for theta, we have to take the arctangent to both sides, because then that cancels and leaves theta. So theta is equal to the arctangent of x, which is what this is. Okay, so and this is what they provided in the hint or the note. So now let's move on. So we take the log of our density, and we get this, and we have a sample size 1. Now let's take the derivative of this with respect to theta. So that drops out, this drops out, then you get 1 over this, and then times the derivative of this. So then that goes away, so you get minus, oh, but that minus is what that is. Then you get minus 2, and then 1 less, and then the chain rule is that's minus 1. We set it equal to 0. Multiply both sides, we still get 0. That's a constant, send it to the other side, we get x minus theta 0. So theta is equal to x. So now we can find the critical region. So here is, if this ratio, now this is maximized over the null, which it's a single value of theta equal to 0. And then this is maximized over the entire space, which we just showed was x. So now you plug in theta equal to 0 here and theta equal to x here, and you get this. Then those cancel, leaving just this. Now, if we take the inverse of both sides, and then the inequality changes, that's what we do here. But instead of calling this 1 over k, I just call it a new constant, k prime. And then we take the 1 over, and that means x squared is less than some other constant. So I just call it c. So x squared is greater than or equals c. That's our rejection region. But now we need to find the value of c, and then we're finished. So the way we set it up is we want the probability of being in the rejection region to be our significance level, 0.05. And that's given in the problem. Now in any, this is a quadratic. So if we have a quadratic and we want the values greater than some c, that means we're out in the tail and out in the tail somewhere, which is this. So we're less than some value, some minus c, because we're in the left tail, or greater than some c in the right tail. That's what makes this happen. So, and if you draw a graph of that, then it's a little more evident. Well, now we integrate that. You know, we have the density of x, so we integrate from negative infinity to c of our density, and this piece right here was in the hint, and that's actually what we just proved up here, that it equals this. Okay, and then this, we're greater than c, so we're c to infinity of our density, and then this piece we know that's a constant, so it comes out front, so that constant is there. And this integral is arctangent of x, you know, the inverse tangent of x. And we plug in our limits of integration. This one here, the pi comes out, and then that's the arctangent of x, plugging in the limits of integration. And now we do that. So we plug in the minus c, and then when you plug in minus infinity to arctangent, remember, as you go this way, this way, this way, it approaches minus pi over 2. So that's what this is. And then the same here. So when you plug in an infinity, it approaches pi over 2. And then that is minus, plug in that, you get arctangent of c. And the pi stays the same. Well, now we start simplifying. So this pi cancels that, and this pi cancels that, and you have a half plus a half. So that's 1. And then this is you can take the negative, so if you just take the negative out, then it's the same. So you get minus arctangent of c minus arctangent of t. So there's 2 of them, but the pi doesn't cancel over that part of the fraction. So you get this. And then this is equal to 0.05. So you take that to the other side, subtract 0.05, then multiply by pi, divide by 2, and you get this. And then 0.95 divided by 2 is this, or 0.475 pi. But how do we solve for c? Well, if we take the tangent of both sides, the tangent and arctangent are inverse functions of each other, and we just get c. On this side, we get the tangent. Okay, so c is the tangent. See, that's our answer. But if you look, it doesn't fit into one of the categories. So we come back up here. This is equivalent to this, but this expression here is also equivalent to the absolute value of x being greater than c, which then that becomes this, and that's the answer. Okay, well I probably did more than I needed to, but it was fun to go through it. Hope you enjoyed it. Please like the video if you did. Subscribe so you don't miss the next one. Thanks, bye.